All right, hello everyone, welcome to the video. This is a very interesting problem because we are going to be trying to calculate how many molecules exist in a modern high vacuum level. So there are some scientific instruments such as the transmission electron microscope, or TEM, or the scanning tunneling microscope, STM. And what's interesting about these microscopes is in modern versions of them, they actually have the ability to resolve matter at the atomic level. You can actually, in some cases, visualize the presence of the atoms. In order to do that, you need to have very low levels of pressure, because especially in the case of STM and also in TEM, you want the system that you're using to visualize the material to not be influenced by the presence of lots of surrounding gas molecules. So you need to use very low pressure, and typical value for these very low pressure systems is 1 × 10 to the -12th pascals, which is of course newtons per meter squared, or pascals. Okay. And I'll just put in parentheses here that this is also the unit of pascals. Okay, and so that's the pressure. These systems sometimes also go down to low temperatures, but just to be different, I'm going to have the temperature of our system be room temperature, which is going to be 25 degrees Celsius. And one thing we're going to need is to convert this actually into units of Kelvin. So I'm just going to do that right now. If you take this Celsius value and you add 273, you will get 298 Kelvin. So we have a pressure and we have a temperature of the gas. And let's just visualize over here in the case of a scanning tunneling microscope. You're going to have some vacuum chamber. There's going to be a surface that's basically composed of, let's just imagine, some atoms that you're trying to visualize. So there's our nuclei. And we're going to have some extremely sharp tip material that's also composed of atoms, of course, trying to basically drag over the contour of these atoms. And it's going to map out the surface of the atoms, and there's some electrical interaction going on here. So I'm not going into the details of this STM, but just to give you an example, if you're trying to drag a super sharp tip over the surface of a structure and actually measure out the atomic scale curvature of that surface, you're going to need to have very low pressure in all this surrounding area. You don't want very many molecules bombarding with your surface at that time. So we're trying to figure out, at this very, very low pressure, 1 × 10 to the -12 pascals, how many actual molecules would there be in a chamber that's maybe 1 centimeter by 1 centimeter, and you can imagine even in 3D here by 1 centimeter. So just for example here, we're going to go per centimeter cubed as our volume. So I'll write that in, that our volume is going to be 1 cubic centimeter. Okay, so the way we're going to answer this is to use the famous ideal gas law. This law is an equation of state for the gas, and it is given as PV is equal to nKT. So pressure, volume, and temperature are the usual variables. This K is the Boltzmann's constant. That has a value of 1.38 times 10 to the negative 23. And the units there are going to be joules per Kelvin. And this N is the actual number of molecules that will be in such a system. So we basically want to solve for N. We're going to have N is equal to PV divided by KT. So if we just plug in our numbers here, we're going to have 1 × 10 to the -12 pascals. Our volume is going to be 1 cubic centimeter, and we also need to do a conversion on that. So 100 centimeters is 1 meter, and we need to cube that conversion factor. So we're essentially dividing by 100 cubed, or 10 to the 6. And then over here, we're going to have Boltzmann's constant to the minus 23 joules per Kelvin. And the temperature here is 298 K. So if you plug all those numbers in, then we will be getting out a nice large number. I can just put that in. Okay, and the answer comes out to be 243 molecules. Which is interesting. So, I mean, if you consider normally you have an epically large number in a typical, sample of gas, you can have, somewhere near Avogadro's number, 10 to the 23rd molecules. At this very low pressure, though, we're down to just 243. And this value was for 1 cubic centimeter, so you could also just divide by 1 cubic centimeter and just get an expression of 243 molecules per cubic centimeter, since the number was for 1 cubic centimeter. So there you go. We have the number of molecules in our ultra low vacuum chamber. And we did it using the ideal gas law, PV equals NKT. Well, that's all for now, guys. Thank you very much for watching. I'll see you in the next video.